Our last speaker is Ala Douba. He is a PhD student at Columbia University. All right, go ahead, Ala.
Hi, everyone. My name is Ala Douba. Today, I'm talking about the role of dispersion degree of nanoclays in controlling the viscoelastic properties of fresh cement pastes. I think the presenters before me made a great job at discussing the different type of nanomaterials, where we basically classify them based on whatever dimensions is greater than 100 nanometer. And I think in all the presentation, it was clear that the agglomeration that's caused by the high surface area of the nanomaterial is the thing that we try to tackle most in our research work. Now, in order to create uniform dispersion of nanomaterials, this essentially entails two processes. First, we need to be able to break down agglomerates into individual particles, and then we need to be able to distribute these individual particles uniformly within the medium. For cement pastes and cement composites, that medium is either water or cement. I think most of the presentations before me were focused on water and solution dispersion techniques, but there's other techniques that we can utilize in which we disperse the nanomaterials into the cement surface into a powder dispersion. Now, when we talk about solution dispersions, there is a time limit for which we can maintain suspension, especially if we're not using any surfactants. And over time, when these solutions are idle, the process of free agglomeration will start. As you can see from the example on the far right of the presentation, this is a nanoclay solution prepared by magnetic stirring, which is one of the common ways to prepare a nanoclay solution. And we can see the excessive agglomeration that causes sedimentation at the bottom of that container. Now, this reagglomeration process causes a decrease in the desired effect that we want to get out of the nanomaterials that we're using. And in order to achieve the same properties, we then have to increase the content dosage. And that increase in dosage will decrease the distance between the nanoparticles and nanomaterials in the solution, which will further drive the reagglomeration process. So this cycle will overall decrease the efficiency of our nanomaterials, especially when used in solutions. Now, the interest of our work, and especially with nanoclays, is that for extrusion-based 3D concrete printing. Now, for 3D printing, we need to have a printing and extrusion system to work, and we need to modify the rheological properties of our material or ink in order to create our 3D prints. And that have been shown by many studies, the efficacy of nanoclays as a rheological modifier. So nanoclays are charged nanorod hydrated magnesium aluminosilicate particles. They're also known as polygerskites or attapulgate clays. The form that I'm presenting here is a commercially available one under the name Actigel 208, and they're basically a highly purified and uniform form of the nanoclays. The nanoclays have a length of 1.5 to 2 microns and a diameter of 30 nanometer. They exhibit negative charges along their length and positive charges along their ends, and that's sort of what creates their interesting rheological properties. When we look at the nanoclay powders under the microscope, we see what we expect as a nanomaterial, that they exhibit high degree of agglomeration. So we see that the agglomerates are on the sizes of tens of microns. And in order to best utilize nanoclays, we need to break these agglomerates into their individual nanoclay needles and distribute them within the medium. Now, dispersion of nanoclays can, as I said, can be done either through solution or through powder. With solution dispersion, we can utilize either magnetic stirring or sonication, and magnetic stirring in literature actually have been the more common way to disperse nanoclays. With powder dispersion, we can either use dry mixing, which is the process of just blending the two powders together, or we can utilize a new dispersion technique that we're presenting here, which is dry dispersion. Now, with dry dispersion, essentially, we create a suspension of nanoclays and cement inside an ethanol solution rather than a water solution. And we use the energy of sonication and shear mixing in order to break the agglomerates and distribute both the nanoclays and the cement within each other. Once we establish our dispersed solution in ethanol, we then go through the process of distillation to recover back the ethanol, and then we further ensure dryness of the cement particles and removal of the ethanol in order to create our nanoclay modified cement. Now, if you're interested in this technique and you want to read more about it, we have a manuscript in Cement and Concrete Composites that is currently in review. So with these nanoclay modified cements, if you look under the scanning electron microscope, we find the unhydrated cement particles have all the individual nanoclay particles distributed on the surface. And with that, we can go and study the rheological properties of cement paste, and we use the vein and cup geometry to do this. Very quickly, the rheological protocol that we're using starts with a pre-shear to break down the structure to its reference state, and then we measure the static heel stress to using a low strain rate. And then we apply a small oscillation amplitude sweep in order to measure the elastic modulus. And we're using the rheological properties to classify the effects of dispersion. Now, the results that I'm showing you now are for cement pastes prepared at 0.3 to 3:4 water to cement ratio. And whenever I refer to the need, that's going to be our reference mix with no nanoclays. So if we first fix the nanoclay content to 1% and examine all 4 dispersion methods, very quickly we can see that the dry mixing of just mixing the 2 powders together is not a very effective way in dispersing nanoclays. When we look at the solution dispersions between sonication and stirring, we actually find that both methods are equally good at dispersing nanoclays, at least when the solution is freshly dispersed. So to be able to study these, we start to focus only on 3 dispersion techniques, dry mixing and stirring, since these 2 methods are the most common methods in literature, and then we add the dry dispersion method that we are introducing here. So when we look at the results of the static yield strength with respect to the nanoclay content, we very clearly start to see that nanoclay efficiency in increasing the static yield stress relies greatly on the dispersion technique. So by using magnetic stirring, for example, instead of dry mixing, we find a higher increase per 1% of nano content. And then with dry dispersion, we find a significantly higher efficiency. And when I'm referring to efficiency, I'm referring to the slopes of that linear line between the static yield stress and nanoclay content. And in fact, with dry dispersion, we can reach increases in static yield stress up to 1,500% from that of our need. What that also translates to is a lower required dosage of nanoclays to meet a static yield stress requirement. So for example, if we want to achieve a static yield stress that is 6 times the increase from that of need, then we will only need to utilize 1.25% of nanoclays using dry dispersion. We would have to use 40% more nanoclays if we use magnetic stirring, and we will have to use significantly more, 190% more nanoclays if we're only going to mix the powders and not do any dispersion techniques. Now, we also measure the storage modulus, and with the technique that we're measuring the storage modulus, we record the storage modulus at strain levels that corresponds to the chemical bonds within our cement suspension. And we can find similar results to that nanoclay efficiency within our cement suspension. And in fact, because with dry dispersion, we start to see this significant more increase specifically against dry mixing, we can start linking these results into a possibly higher increase in CSH nucleation or rigidification. Now, because we are now able to establish a uniform dispersion of our nanomaterials onto the surface of cement, this allows us to study cement paste in systems that are not friendly to disperse nanomaterials in, such as kerosene. So for example, we can study cement paste in this kerosene suspension, and we can classify the static yield stress and storage modulus. What this enables us to do is to go and study the mixed interaction forces that are present in the, between nanoclays and cement. And because we are now using kerosene, that eliminates all the dissolution products that we would have and all the forces coming from the solution products. And that will allow us to further classify the mechanics of how nanoclays and cement interact within colloidal suspension. Now, with respect to 3D printing, if we focus on the individual layer thicknesses that we can achieve with the static yield stress, we start to see not only do we lower the dosage required to achieve these layer heights that we want to see in our printing, but in fact, we will be able to achieve significantly higher layers. So if you see on the figure on the right, the mixes that I'm showing are between magnetic stirring and dry mixing are the highest dispersible amounts of nanoclay that we can use. So these in turn translate to the highest individual layer thicknesses that we can use within cement-based systems, and we can exceed these using dry dispersion technique. So in conclusion, and I know I'm rushing through this because we're out of time, I hope I was able to show you that nanoclay's effect on cement rheology depends on the dispersion technique and the dispersion energy that we use, and that the new dispersion technique that I introduced, which is dry dispersion, is highly effective in coating the cement particles with nanoclays. And because of that, it allows us to study the interactive mechanisms of nanoclay in cement composites and suspensions. And that finally, by creating a high efficiency dispersion method, we are able to decrease the nanoclay content required to meet the 3D printing stresses and dosages required. So this work is funded by NSF Career and was done with the help of Carleton Labs. Thank you so much for your attention. If you have any questions, I know we're out of time. You can send me an email and I'll be happy to respond to your questions. Thank you.
All right, thank you, Ala. So I see a question in the Q&A. I don't know if you can see, but it's pertaining to how salts could affect the particle's clay morphology.
For that, I'm actually not sure. We did not really focus on salts within our study.
Yeah, I can kind of maybe, well, yeah, so we haven't looked at that, but I don't know, Ala, if you shared this in your presentation, but we're working with highly purified clays that remove swelling clays. And so I know salts can affect swelling clays, but that's not the type of clay we're using. So we can maybe expect the effects to be minimal, but maybe that's something that we should consider going forward. All right, thank you, Ala.